Mm. Okay. Today we continue our lectures now devoted to the justification of the general facts about abstract chaotic expansion of Gaussian functionals, form of stochastic exponent and a joint operator, which is called extended or square-root integral, in the special case. Let me recall the main steps of construction. So now we are considering Hilbert space H in this specific form. This is space of square integrate regulated functions on the interval 0, 1 with the usual scalar product. And here we considered special case of Gaussian white noise generated by the Wiener process. So suppose that W small is a standard Wiener process. And define for any H which belongs to our space. So H is a square integrate function. Define the product H psi with this generalized product element as follows. This is integral from 0 to 1 Hs dWs. We discussed already that this integral is properly defined. For example, when approximating function h in this space by the step functions, it occurs that corresponding sums converging to some limit, and this limit is exactly the definition of this integral, and it is Gaussian random variable, and it satisfies the following: its distribution is 0 norm of h square y. So in this way we define Gaussian white noise with space L201, and we began to discuss the main operators, main tools of Gaussian stochastic analysis in this partial case. Why this discussion arises? The reason is following. Let me recall you that we already have a well-developed theory related to Ito-Wiener integration. So then we can properly define Ito-integral. Here is integral from 0 to t xt dw xs dws, where x is adapted to ft equal sigma field generated by the past of the Wiener process. And square integral. So we have the expectation of integral from 0 to 1 xs squared ds is less than infinity. Then such integral is properly defined with the approximation by the special step functions and has good properties. We recall just a few of them which is necessary for our considerations. So we wrote that expectation of the integral from 0 to t xs dws is equal to 0. Expectation of the square of this integral xs dws square is equal expectation of the integral from 0 to t xs square ds. And the Ito formula holds. So if we have a smooth function which has two continuous bounded derivatives, then we have the following. This function from the integral from 0 to t x s ds here t is equal f 0 0 plus the terms which are firstly similar to terms which arise, for example, in Newton-Leibniz formula. So here is integral from 0 to t f prime with respect to the first derivative. I don't write the arguments. Here we have x s and dws plus the same term integral from 0 to t f prime with respect to second argument, here dt, and it occurs that we need additional term, which is sometimes called eta term. It is 1/2 of the integral from 0 to t f 2 prime with respect to the first argument, and here is xs square ds. This new term arise due to the properties of the Wiener process. Of course, the integral with respect to Wiener process has a lot of properties, good properties, which we don't mention. For example, it is a continuous martingale, it's suprema can be estimated using the estimation of x. It is a local in some sense with respect to arguments from probability space and so on. But this is what we need. And from this point of view, it is interesting to relate this construction and consider such well-known Wiener functional as a solution to stochastic differential equations to relate to our general and very abstract picture which we developed for the functionals from Gaussian white noise in arbitrary separate Hilbert space. So we begin with this, and the first question which arises here is the Hautic expansion. What is the precise form of its members here for square integrable random variables which are measurable with respect to Wiener process? On this way, we found some interesting things. Namely, we discussed the Hautic expansion of the very specific random variables of the stochastic exponent of the following type. Let us consider E lambda t, which is equal exponent w lambda wt minus lambda square over 2t. We know that this is stochastic exponent, which is related to the following vector h. So in our previous notations from the abstract picture, this is lambda indicator of 0, 1, 0 t, 0 t. And consequently, we know that it is expanded as follows. can be expanded as follows. The sum from n equals 0 to infinity. Here is lambda n over n factorial t in n over 2 power, and here is hr, Hermite polynomial, and here is wt over square root of t. So we know such kind of expansion, which we already studied well. But from other side, last time we obtained another representation for this random variable based on the fact that it is easy to see using Ito-Wiener that this random process as a process from the parameter t satisfy linear stochastic differential equation, which is very similar to the equation for the usual exponent when d e lambda t is equal lambda e lambda t dwt with the usual initial condition d lambda 0 equal 1. So this explained by the way the name, because this equation is very similar to the linear equation, ordinary differential linear equation for usual exponent function. If we put here dt, then we get exponent lambda e. So using this fact and iteration method for solving this equation, we got the solution as a series of multiple Wiener integrals. Namely, we got the following expression that it is equal to the sum from n equals 0 to infinity lambda n. Here is integral delta n from t dwt1 dwtn. And let me recall you that this delta nt, this is simplex where the coordinates t1, tn are ordered in increasing order. So this is the simplex which contains such t1, tn, then 0 is less or equal to 1, less or equal to 2, and so on, less or equal to less or equal to n, which is less or equal to t. So due to this ordering, one can see that this integral is properly defined as Ito-stochastic integral, but it is very, very easy case. And as we mentioned, it, Wiener was first who discussed such kind of integrals. And due to such two representations, which are valid for every lambda from the real line, one can easily, this can be a good exercise, by the way, check it that these coefficients must coincide. Why I am saying that this is still exercise? Because both these series are convergent in L2 sense and has orthogonal summands. But still it is good, and due to this one can get the following formula. Here is t in n over 2 power divided by the n factorial equals the integral from delta n t dw1 dwt n. Of course, oh, excuse me, I forgot here Hermite polynomial. So t n to the power over n factorial multiplied by Hermite polynomial degree n from wt over square root of t is equal to this expression. By the way, it can be done by induction using Ito formula and relationship for derivatives of Hermite polynomial. It can be also a very good exercise to check this in a different way that we did. But there is we have such relationship, and this relationship allows us to make a hypothesis that maybe, in general, members of the harmonic expansion are some kind of the Wiener integral. It is true, but to make it more visible, let us rewrite slightly the right hand side of this formula, part of this formula. What I'm going to do? Consider sigma, which belongs to the set Sn, where is a set of all permutations. On one n. So this is, in other words, a set of all projections. This set of itself. Then it's easy to see that this is just a matter of notation, that it can be written as follows. It is equal to the 1 over factorial, 1 over factorial. Here is the sum over all sigma, excuse me, over all sigma which belongs to Sn. And here I'm writing integral delta n t, and I will write here sigma from this set. What does it mean? It means that we are considering again simplex, but I change the number of coordinates. So now I will write dwt sigma 1. It will be the smallest coordinate. Dwt sigma 2, and so on. Dwt sigma n. So there are n factorial possibility to order indices, and I defined for any special ordering of indices simplex where the ordering of indices is transferred to the ordering of the coordinates t sigma 1, t sigma 2, and so on. So this is smallest one, this is just bigger than this, and so on. It is evident that all these integrals are equal to this, because this is just matter of notation, and we remember from the first year calculus that the value of the integral doesn't depend from the name of the variable of integration. So this formula holds, but see what happens. If I consider the following union, the union of all sigma which belongs to Sn, the union of this sigma delta n t. Then what we will get? What we will get? You see, here we have special ordering between coordinates. And of course, if I take arbitrary set of numbers, for each of them belongs to interval 0 t, then I can order these numbers in some order related to some permutation. So it's easy to understand that this is equal to this one. Yeah. From this point of view, it is useful to give such a definition. By the way, this is definition of the multiple integral over such a cube. So now I'm considering the following definition. The integral n times over cube 0t dwt1 dwtn is a sum. Oh, let me do it by the form. This is a sum over all what you have to rewrite all permutation integrals, multiple Wiener integrals over such simplices. So this is a definition. Why I'm so emphasizing that this is a definition? Because in this formula we have no adaptedness in general between different random values. Yes, it can happen that we need to integrate over dw t2 the value of which is greater than t2. Yes, but we don't do this at all. We don't use some Ito construction there. We just define this integral using Wiener integrals, which are properly defined, but using the set of simplices, which in the union gives us this domain of integration. So this is a definition of the such kind of stochastic integral. And when we do it as follows, it became to be more close to our previous investigation. Why? Because one can say that it is related. One can say that it is related to special kernel here. I can put here 1, and I can write this. I can write this as a special kernel, as the integral from the special kernel. It is the integral from 0 to t, and here is indicator of 0 t from t1, indicator of 0 t from tn, dwt1, dwt1, dwtn. And of course, then I can put here 1. And let me denote this by an t1 tn. Of course, this is a very simple function of the variables t1 tn, but what I just said, it is a symmetric function over all permutations. Yeah, and when we have such a notation, one can imagine that maybe we are very close to our goal to connect abstract construction from the general hyperspace and generalized Gaussian random elements there to the case when a noise Gaussian random element is generated as a formal derivative of the standard Wiener process. Why? Because now when A is a symmetric function, one can naturally ask why we just concentrated on this special form of the symmetric function an. So one can try to look at a more general definition of such kind of stochastic integral, and one can try to consider the following. Suppose that function an belongs to L2, 0, 1 in n power. So this is this function is square integrated on the cube and symmetric. So it is symmetric over all permutations of the coordinates. Then one can try to consider the same kind of stochastic integral with respect to multi-stochastic integral with respect to Wiener process. Maybe one can consider the following definition that the integral from 0 to 1 times an t1 t1 tn dw t1 dw tn is equal to the sum over all permutations of our group of permutation Sn. Here is the integral with respect to sigma of delta n. I will not write here 1 because we usually consider the interval 0, 1. And here we have Hn, T sigma 1, T sigma n, and dw T sigma 1, dw T sigma n. And of course, this is just definition, but we can continue writing using symmetricity of an with respect to permutation of arguments, and then one can say that this is n factorial, and here is one integral n t1 tn dw t1 dw tn. Since we have the following definition, it will be good to calculate some moments of this integral and it can be easily done because we remember that this is simplex delta n. So we have here exactly Ito case, and we know what is the expectation of the Ito integral, and we know what is the expectation of the square for Ito integral. So we know everything. So let me do such calculations. It is simple now. So we can see that expectation of this multi-integral an. I will write here arguments dwtn is equal to 0 because here we have expectation of eta integral which is equal to 0. Expectation of the square of this integral in factorial and an dw t1 dw tn is equal to what we have seen. We have here n factorial is just number, so we have its square, n factorial in square multiply onward. You remember we recalled this in the beginning of our lecture today, that expectation of the square of the Ito integral is just usually back integral of the expectation of the square of what is inside. Yes, but what we will have inside? We will have inside the same integral, but with respect to the simplex n minus 1. So we will continue to do these expectations. And finally, we get the formula integral of the simplex delta n, a n t1 tn square dt1 dtn. And now let's continue calculations because we remember that this function is symmetric over all permutations. So I can substitute this integral of a simplex by the integral of a cube, just taking 1n factorial, because integral over all simplices, integrals over all simplices of these expressions are equal. So we have n factorial of such integrals equal to the integral of a cube. Finally, we get the following expression. It is equal n factorial, and here is integral 0, 1, n, a, and t1, tn, square dt1, dtn. Okay, so we see that we have something very similar which we considered in general case. Let me recall you that now we have the following relationship. An belongs to A2 0 1 0 1 and power symmetric power. But if we consider this space from the point of view of functional analysis, it is not hard to check again as an exercise that it is exactly the tensor power A2 0 1 symmetric one. So maybe we get the desired correspondence. You remember that when we discuss the general construction, then we considered AN, we considered AN, which belongs to H and symmetric. We say that AN is symmetric and linear Hilbert-Schmidt form defined on H, and then we start. We define AN from psi, which was the special construction of substituting of our generalized random element into AN. We use it orthogonal basis expansion and substitute the powers of Gaussian random variables by Hermite polynomials. We remember this, but finally we get such a kind of expression, and and we know that expectation of this expression is equal to 0. Expectation of the AN psi square is equal to the norm of AN Hilbert-Schmidt norm n square multiplied by n factorial. And you see exactly the same we have here. Expectation of the multiple integral 0 to 1 and an small dwt1 dwtn is equal to 0. Expectation of the integral from 0 to 1 and an dwt1 dwtn square is equal to n factorial, and here is exactly the same Hilbert-Schmidt norm integral an square dt1 dtn. Moreover, we remember the procedure of definition of this quantity, and at least for the very simple case, but very important, when h is equal to integral indicator of 0t, we have that now. We discussed this already today and previous times that if we define an now as h as a power, so it is exactly the kernel which is equal to 1 when all coordinates is less than t. Then we have the equality h n psi. It was Hermite polynomial, you remember, is equal to the integral from 0 to 1, and here is h n power dwt1 dwt. So we have some similar properties. We have such equality for such family of functions, and now it is just a technical job to check that the same is true for arbitrary square integrated symmetric kernel and small. I will not do this in all details because it is a rather technical job. but maybe you can imagine that using this function for any t, we can organize step functions which will approximate symmetric kernels and do the necessary jump. Please check this by yourself as again as an exercise, but it is rather technical. But after this, we can finally say that now we have the following good chaotic expansion for square integrate functionals from the Wiener process. Namely, we have the following. We can consider the random variable alpha, which is measured with respect to sigma fields generated by W, and such that it is square integrate. And then we can say that alpha can be uniquely represented as the sum from n equals 0 to infinity, and here is most integral from 0 to 1 n an t1 tn dw t1 dw tn. Moreover, we have now a relationship that a0 it is the member of the series related to 0. There are no intervals there. This is just number, and a0 is equal to expectation of alpha, and expectation of alpha squared is equal to the sum from n 0 to infinity n factorial multiplied by the integral here n integral an t1 tn square dt1 dtn, and an are symmetric kernels. So this is chaotic expansion in our partial case related to the noise generated by the Wiener process, but sometimes people prefer to write this expansion in terms of Wiener integrals. And you remember that we define this quantity formally using sum over simplices, and this sum was very simple because this function is symmetric, so all those Wiener integrals are equal, and then one can continue and write this as follows. This is sum from n equal 0 to infinity, and here is n factorial integral with simplex delta n an t1 tn dw t1 dw tn. This representation is useful, and sometimes it is called Ito-Wiener expansion for random variable alpha. We will use the same name for all for these two representations. This is an Ito-Wiener expansion. For alpha. Of course, this n factorial can be put it here, and we can just write this is a n tilde, and forgot that this function must be defined somewhere outside of this syntax. So this is a Ito-Wiener expansion, the analog of logic representation for square integral functional from the white noise. It must be said that despite of this name, which came from the probability, of course, this expansion was firstly written by such authors Cameron and Martin. As I remember, it was 1948 or 1947. I don't remember exactly 8 or 7 here. And they worked purely in functional analysis stuff, so they don't discuss Ito formula, don't discuss any Ito integral, because Ito integral was defined slightly later. They discussed a representation of the square integrated functionals defined on the space of continuous functions, which is equipped with the Wiener measure. So they considered the same problem of the orthogonal representation, just from the point of view that we have some Banach space, the measure, probability distribution in this Banach space, and we are asking what is the orthogonal polynomial expansion for the square integrated functions. And they discovered the same construction. Of course, they don't say that these are some kind of Ito integral. Yeah? So now we have such an expansion, and it is good to begin to ask what does it mean the stochastic derivative of the random variable alpha, and what is the adjoint operator to in this special case. Let us see what we have in this special case. So now we begin to consider the operators of our stochastic analysis in this partial but very important case. So let me consider. Now let me begin with stochastic derivative. What is d alpha now? As we said, in general, let me recall the general definition. If we have H, we have psi there, white noise, and alpha is square integrate, then alpha has a unique chaotic representation. And then we just have the following definition. D alpha must be the following element of K2 omega pH. So this must be a random element pH with the square integrate norm such that we have the following relationship. For any H, small which belong to H capital, the scalar product d alpha H must be equal to the sum from n from 0 to infinity. Here is n, and here is a n h. But now here is n minus 1 arguments. Yeah? So we have such a construction, and now let's adapt this construction to our partial case. So now we have H201, psi is generated by the Wiener process, and instead of this Hilbert-Schmidt multilinear force from psi, we have multiple integrals with respect to Wiener process. So let's try to do this. And now we have the random variable alpha, which is measured with respect to our standard linear process W, and alpha is square integrable. And now we have the representation of alpha as a sum from n equals 0 to infinity, and here we have those multiple integrals which respect to Wiener process which we defined already from the symmetric kernels Tn, dwt1, dwtn, and these kernels are symmetric and square integrable. And now, what is the definition of the stochastic derivative? D alpha must be is square integrate a random function. Yes, a random function. Because now, what is the space H? Space H is the space of square integrate functions. D alpha must be random element there. Moreover, it must be a random element which has a finite second moment of the moment. Square integrate random function. And now, for any H which belongs to 201 and 201, we must have the following equality that integral from 0 to 1 d alpha, I will put here additional brackets, d alpha t h t dt must be equal something n equals 0 to infinity, and here what we will have? Of course, we will have a multiplier m. Then I will substitute in our form, instead of one argument, h, which means in our language now that we have one integral with respect to dt. So I will put the integral 0, 1, and since everything is symmetric, then I will use Tn as this variable htm, which I now denote by t symbol in order to keep the same notation. Here we have the multiple integral from 0 to 1, but n minus 1 time, and here we have, unfortunately, I have to revise this, and here we have the following an T1 Tn minus 1 T dw T1 dw Tn minus 1 and dt. I can put the brackets, and then what is remaining? It is remaining just to put this sum inside. I can do this because remember that summas are orthogonal in two sense, at least in two sense I can do this. So finally, I will get the following. That it is equal to integral of 0 to t ht on the following sum from n equals 0 to infinity, n here is integral n minus 1, 0 to 1, h n t1 tn minus 1, t dw t1 dw tn minus 1. Okay, so from comparing left-hand side and right-hand side, one can conclude that now stochastic derivative, the random variable alpha, is the random function which is represented as follows: d alpha d. And now, because we understand, firstly we get stochastic derivative, and this is the argument, one can get that this is equal to the sum from n equals 0 to infinity, and here is the same integral from 0 to 1 n minus 1 an t1 tn minus 1 t dw t1 dw tn minus 1. That's all. So now we understand what is the expression for stochastic derivative of the random variable alpha in terms of the elements of Ito-Wiener expansion. So now it's time to consider some examples of stochastic derivative, and we will see some familiar formulas, but we will do this next time. For today, this is all. Thank you for your attention. Maybe somebody have questions or some comments, please. Okay, if there are no questions, thank you for attention, and see you next week. Bye.
Thank you, bye.
Thank you, bye.